And sorry for keeping you from this beautiful weather. I will talk about something called hash-based signatures. And this is actually among the first signature schemes that people came up with. And so, like many of these post-quantum schemes, this actually dates back to the late 70s. So the actual paper by Merkel was only published in 1989, but I think the first proposal for a hash-based signature scheme was in 76 by Lampert. And well, these things are interesting because they are inherently post-quantum, because you only need a secure hash function. And they only need a secure hash function, which is nice because you don't need some additional assumption. Like, you don't have to suddenly think about coding theory or about lattices. You just can stick with the stuff that you actually already know. And this means the security is quite well understood. So most of you just started, but if you followed a bit the cryptographic discourse, you might have noticed that some time ago, before this post-quantum competition, we actually had the SHA-3 competition because SHA-1 got broken, and SHA-2 was essentially SHA-1 just with bigger states, so the design is pretty much the same. And so the community started to actually look into this, and such a competition actually generates a lot of knowledge and understanding. And so that for that reason, we actually know pretty well what a hash function should be and when it is secure and how to analyze it. I'm pretty sure if we had a new competition, we probably would again find even more stuff, but for now, this is probably better than for many schemes. In general, if you have stateful schemes, about which I will talk in the beginning, hash-based signatures are extremely fast. There's more recent stuff, which is stateless, which will become the new SLH DSA standard, which was Sphinx Plus, which was selected in the NIST competition as one of the signature schemes. That is not necessarily faster than most other schemes, to put it this way. So verification is actually reasonably quick, but signing takes a bit more than many of the other schemes. Well, and actually the schemes are already standardized. So we have stateful schemes, XMSS and LMS, for which we have RFCs. And so these were essentially the first post-quantum signature schemes that got standardized. And as I said, Sphinx Plus is currently being standardized by NIST. The standard draft is, I think, stable and done. There is a good chance, Bas mentioned that he heard somewhere that they might publish the standards on the 10th of April. Not sure, but there would be also nothing that really keeps this back. Like, there was a public comment period last summer, and since then, at least for the hash-based stuff, nothing really changed. Okay, so let's take a step back. Some people say these schemes have minimal security assumptions, and the reason is the following. You can look at this from 2 points of view. The more practical point of view is, if you look at any digital signature scheme that you will see this week, you need a cryptographic hash function, and then you use some additional intractability assumption. You'd use syndrome decoding, which we had yesterday. You can use SIS, which you will see tomorrow. You can use the MQ problem, which you will see on Friday. But in the end, you have some hard, or presumably hard problem, and you need a secure cryptographic hash function, right? This is what we also have classically, like RSA, the DLOG-based schemes, and so on. They all have this additional assumption. If you look at hash-based signatures, actually this side goes away. You really just need a secure hash function. And especially if your signature scheme is proven secure in the random oracle model, then really there's nothing different. Like from the random oracle model, we can get all the properties that we actually need for our hash-based signatures. So let's dive a bit deeper into what a hash function family actually is. So For certain notions, we actually have to define families, because if you just define this for single functions, this doesn't make sense from a complexity theoretic point of view. So we think about a keyed function where the key is public. You can think of this as a function description. You can think about this in practice as the initialization vector, which goes into the function in the very beginning, and it's just hard-coded. And if you would switch this, you've got a different function, but still kind of the same description. And then, in addition, it takes an input x, right? And so this key will usually be just as a subscript, and we assume that you can efficiently evaluate hk of x. And I will use this trapeze. I don't know what the English term is. Trapeze? Trapezar. Okay. To depict it. So, let's go through the notions. You might have seen most of them. I will just give a bit more of a formal description. So, one-wayness can be described, so this is the hardness of pre-image finding, and you can describe this as a game where an adversary gets a description of the function, k, and a value y, or a challenge value y, which is computed as follows. I'm sampling a random key, I'm sampling a random x, and then I'm evaluating the function hk at x. Right? This is important because this says this point actually has a pre-image, which is not necessarily true if I just sample a random domain element, range element. Well, and then I give the key and the computed output to the adversary, and the adversary wins if they come up with an x which maps to this y under k. Doesn't have to be the same, that's not the point, it just needs to be another pre-image of this point. Or the same. The next more well-known notion is collision resistance. So collision resistance just intuitively says I cannot find two inputs which map to the same output. And this notion actually you cannot reasonably define without a function family. Because otherwise if I talk about a single function, there exists a trivial algorithm which breaks this, namely one that has the collision for this function hard-coded and just prints it every time. It has runtime 1, so there's no notion from a complexity theoretic point of view that this is hard. But if I'm sampling a random key and you have to give me a collision under that key, then this actually becomes hard. Of course, in practice, we still don't know how to find a single collision for SHA-3 or SHA-2, so we don't know how to generate this algorithm which has this collision hard-coded, so in practice, this is still not an issue. And then we have something which is in between these two notions called second pre-image resistance, and that says it's hard to find a collision for a given input. So I'm sampling a random domain element and a key, and I ask the adversary to output a second domain element such that these two values collide. And that is kind of the standard stuff that you hopefully have seen at some point in a crypto lecture if you took one. We actually introduced a decisional version which helps to do some proofs in a nicer way. And that asks if there actually exists a second pre-image, or if the point just has one pre-image. If you have a massively compressing hash function, then this doesn't matter because you always have more than one pre-image with overwhelming probability. But if the function is actually length preserving or just mildly compressing, then there is quite a high chance that you sampling a random x will hit one which doesn't have actual collision in the function at all. Okay, and then we have two notions which are a bit less common. Undetectability is something like pseudo-randomness of a hash function. So here, this is described by a game where the adversary, like for one-wayness, gets a key and an image, y. The difference to one-wayness is that this is a distinguishing game, not an extraction game. or search problem. So in this case, the adversary either gets the image of a random input, or it just gets a random element from the codomain. Okay, and it should be hard to distinguish these two, which essentially means the outputs of the hash function should be uniformly distributed in the output space, and we cannot really distinguish the image of the hash function from the uniform distribution over that space. Again, if you have a massively compressing function that is somewhat random, then this is trivial, but if you have a length-preserving function, then this actually is not necessarily the case. And the last notion is pseudo-randomness. So this is the only notion where actually the key becomes secret. And this notion says if you don't know the key, so you don't know the description of the function, then you cannot distinguish this function from a random function by just looking at its input-output behavior. So this is something we describe by a game where the adversary gets access to some black box oracle. So if you're more from the computer science side of things, then think about this as a remote function call. You do not know how this thing implements what it does. You just know it implements some function. And you have to promise that this function is either some random function or it is an element from the function family for a random key k. And you can send their points and you will get back the images of these points. Okay? And this is something that we use quite a lot to replace random values by pseudo-random values. You can run this thing in counter mode, so you just feed it 0, 1, 2, 3, 4, 5, and so on. And thereby you can generate a pseudo-random sequence. Yeah, this is more or less the main thing that we do. Any questions about these? Okay. If we talk about the security of hash functions, we usually talk about generic security. So we look at what is the best that an attacker can do anyways. Right? So if I treat a hash function as a black box or a random function, then which attacks are the best that I can actually run? For pre-image search, I can just do brute force search. At some point, I will find an input that actually maps to my Y. I will succeed, and I can do this for all properties. And I say usually a hash function is insecure, like a practical hash function, the moment it's too far off from the generic security amount. So if you find, for example, SHA-1 was considered broken the moment we had a 2 to the 60 attack, I think it was 2 to the 64 complexity attack instead of 2 to the 80. Which some people might say, yeah, this is just 16 bits off, this is not too much, but actually, at that point we also didn't know yet that we can practically exploit this necessarily. But it was just clearly off the theoretical limit, and then you know there might be better attacks possible. And what we usually do, in contrast to what Alex did this morning, we do not necessarily count bit operations, but we simply count the number of queries to this hash function that you actually need to attack it. Because that makes our life a lot easier. And you're just off by a factor like 2 to the 7, 2 to the 8, depending on which hash function you're talking about. Okay, so I said this before. Generic security for a one-way function. All the best I can do is actually random guessing. So if I do not do any query, the probability for a random function, if I'm just outputting a random value, that's the best I can do without any knowledge about the function, that will hit with probability 1 over 2 to the n if I have an n-bit hash function, so with n-bit outputs. Right? If I have a single query, then I can actually check my first guess. So I take a random value, I feed it to the hash function. If this hits y, I'm lucky. If it doesn't, well then I output a random element. And I can compute this over and over, and so with Q queries I end up with Q plus 1 over 2 to the n. And so in total we end up with complexity of a successful attack of 2 to the n. So if I want to reach anything which gets close to 1 in success probability, I have to make order of 2 to the n queries, and actually I can show with this attack I will also reach this. The quantum case is a bit more annoying, because what we just did was essentially a counting argument, and we look at how much success probability we can accumulate per query. You can, in some cases, do this also for the quantum case, but then the methods get more complicated. So you can do what Chris mentioned, the polynomial method, which tells you how much amplitude you can actually accumulate on a value that you're interested in per query, and then you use this amplitude amplification, which Grover uses internally to bump up this amplitude. But in general, we can actually look at bounds for known problems. Like we look at the Grover bound, and then we can give a reduction proof which says, okay, if you can actually find a pre-image for my random hash function, I can show that then I can use this algorithm to actually solve random search for Boolean function, and this is exactly the problem that is solved by Grover, and for that we actually have bounds. Right? And so then I get the query bound of 2 to the n over 2, and this is also met by Grover. And there are actually some smaller terms happening in both cases, but they vanish the moment you have 2 to the n much bigger than 2 to the n. And so the bounds in general, classically, for all these problems except collision resistance, are 2 to the n, and these are actually type bounds matched by text, but I didn't have a theta. And these go down to 2 to the n over 2 at the quantum case. For collision resistance, the classical bound is 2 to the n over 2, and there's an algorithm called EHT from Bassar, Hoyer, and Tapp, which actually show you can do this with 2 to the n over 3 quantum queries. There is a bunch of details there, so that algorithm actually also has 2 to the n over 3 storage, which has to be quantum accessible storage, so this makes things really nasty. There was a bunch of works that I think Andreas was also involved in that improved the required amount of storage, but then you're paying in runtime. So collisions are not as much easier as it might appear, because you always have these storage requirements in the quantum setting. In the classical setting, we actually have an algorithm which does the 2 to the n over 2 with essentially no storage. So there's this polar draw method which actually needs, I think, to store 4 hash values. 2. I think 2 hash values are enough. And you still do 2 to the n over 2. And this gap in the security is actually something that's also reflected if you look at these properties from a complexity theoretic point of view. So pseudo-randomness, undetectability, one-wayness, second pre-image resistance, they all live in a space called minicrypt. And you can actually build one from the other. So there's a second pre-image resistant hash function. If it's massively compressing, it's also one-way. You can build a second pre-image resistant hash function from a one-way function. You can go from a one-way function to a pseudo-random function and vice versa. The only thing that's clearly in a different league is collision resistance. That is something that we do. We cannot build from one-way functions. There's a separation which shows you cannot do this. And so this is really, from a complexity theoretic point of view, significantly harder. And as we've seen also, the attacks are significantly better for collision resistance than for the others. And this is also reflected in practice. So if you look at the attacks we had on hash functions in 2004, we had theoretical collisions against MD5. in 2005 we had the theoretical collisions against SHA-1, so these were both the cases where the actual attack complexity dropped below the generic security bound. Then in 2008 we had the first practical collision of MD5, and in 2017 we had this, was it hash clash? I don't remember. So the people from CWI, Mark, currently don't remember the second name. So he did some certificate forgery attacks with MD5 and then also presented the first SHA-1 collision in practice. And the funny thing was they wanted to put this into Git, and the problem is Git uses internally SHA-1 to actually compare files. So if you have a file that has a SHA-1 collision, Git is not very happy. Yeah. So this is maybe telling you if we have these theoretical attacks and they really have some attack ideas that are showing there is some structure that you can exploit, there's a good chance that you actually get this into practice within not too much time. The interesting thing is, for both of these functions, so even for MD5, we do not have any real clue how to go for second pre-image or pre-image attacks. This is really a whole different business. These collision attacks exploit that you can actually choose both messages, which you cannot do in this case anymore. Right? And so, I mean, I'm not into symmetric key cryptanalysis, but what I heard from people from the community is really no one touches this really because it's just too hard. Okay, so maybe as a brief primer, why did I tell you this? You want to stay away from collision resistance if possible. Because collision resistance is easier to, or breaking collision resistance is easier than the other stuff. And one thing that comes from the easier or better attacks is that you actually need longer hash function outputs to achieve the same level of security. Right? You need twice the output length if you need collision resistance compared to if you need any of the other hash function properties. Okay, so let's look at some signatures. So the first proposal was by Lampert and I think Diffie independently, so people just say Lampert signature. The idea is I have a one-way function h, I have a message which I can split into bits of length m, and then I denote n-bit blocks by these rectangles. And so my secret key consists of 2m random bit strings. So those I just sampled uniformly at random. I group them into pairs, and every pair has a 0 element and a 1 element. Right? Then I hash these, and the resulting hash values form a public key. And then I simply, if I want to sign a message, pick one element from each of these pairs and publish this as a secret, as my signature. Does anyone already see why this is something called a one-time signature?
Yeah, it's because after you publish it, anyone can just reproduce your results.
Well, after you publish it, everyone can reproduce the result. That's the whole idea, because I mean, this happens with any signature, right? Nah, not entirely. So in this case, you're just recomputing actually the verification is indeed just checking that you get that you hash these values to the public key. But of course, you can output the signature then. Yeah.
Yeah. So if half the keys are known, so like if you have a random new message, then half of them will already be known.
Yes, so actually if I have two random messages, on average like 3/4 of the secret key will be known. And I can sign any message which maps into these. And if I can choose the messages that I want to be signed, then I can ask for the old 0 string and the old 1 string, and I get the full secret key. Or any two complementary messages, like gives me all of the secret key. Right? And then I can sign an arbitrary message. So this is what's called a one-time signature, where you can sign one arbitrary message, but per key pair, but not more. If I sign more than one message, my security is really gone. Right, and so verification is really just, I take the signature, I hash it, and I check that it maps to the right public key values. That's everything. Any question? No? Good. And if I don't see you with a question, then just scream. Okay, so luckily I explained the security notion for signatures yesterday. The difference for one-time signatures is, of course, I only get a single query to the signing oracle. Right? So if you remember, security meant the adversary gets a public key and then sees signatures of you, and afterwards still cannot produce a signature on a new message. In this case, obviously, if the adversary would see more than one signatures under the same secret key, this would be trivial, so it only sees a single signature for a message of their choice, and then has to come up with a new signature on a new message that exists. And for Lamport-Diffie, this property holds as long as the hash function is one way. And I kicked out the proof. Actually, why does this hold? Intuitively, what you do is, if you're getting an image which you want to invert, you put this at a random position in the public key. When the adversary asks for a signature, you hope that in that pair it actually took the other bit, so you have to publish the other secret key value. And then later, when they publish a forgery, the forgery has to, or the message that gets signed, has to differ from the message they asked for before in at least one bit. So with probability 1 over the message length, this will be exactly the pair in which you put your image, and then they have to give you a pre-image. Right? And that way you can show that with a reduction loss of 1 over 2m, or a factor 2m loss, you actually can use an attack against this scheme to actually find a pre-image in one-way function. Okay, now one-time signature scheme is of course not very practical. If you think about it, to use this, I have to somehow securely get a public key to the other party. I could also just bring my message securely to the other party. So the only thing I can get is that I maybe get some delay, so I can, when we meet, exchange one-time keys and later on use them to actually sign. But this is not extremely practical, so we would like to actually have a compact public key that we can use to sign many messages. And this is where Merkel's contribution comes in. So Merkel proposed, well, you start from a one-time signature scheme, and then you use many instances of this one-time signature scheme. You take the one-time public keys, and you authenticate these using a binary hash tree. So this means the leaves become the hashes of these one-time public keys, and then I take any two neighboring nodes, hash them, again take two neighboring nodes, hash them until I arrive at a single root node. This thing becomes my public key, and the one-time secret keys become my secret key. Actually, these things I can generate using a PRF in counter mode, because these are all random strings, right? There's no structure in it or so. So I can just start from a short seed or short PRF key and generate all this data whenever I need it. So I get short secret keys, short public keys. How does a signature look? Well, I have one-time signatures. This means I actually have to make sure that I'm not reusing any of these one-time key pairs. So what I do is I use them from left to right. You can also use them from right to left if you prefer, but The main thing is you establish an order, you use the keys in order, and then the signature contains the index of the one-time key pair that you're actually using. Let's say we are at position 2 now, so we put a 2 in there. Then we add the one-time public key and the actual one-time signature on the message. And in addition, we have to add these nodes in the tree, which are the nodes that the verifier needs to actually recompute the public key. Right? So if you see a one-time public key and have these nodes, from this one-time public key and this node I can compute this value, from this one-time public key I can compute this value, together with this node I can compute this value, together with this node I can compute this value, now with this node I get the public key, which gives me essentially a candidate for the public key, and if these two match, I know the one-time public key was valid. In addition, I verify the one-time signature, and then I'm done. And this is actually called an authentication path, and if you remember yesterday I said you can open all but one leaf with an authentication path. So just as a remark, switching context to keep you awake. If this is a seed, these are PRGs, the arrows go in the other direction, so I'm actually generating stuff. Then if I'm publishing these nodes, I can compute all leaves except this one. Right, so I can compute all leaves except the one which now is the one-time signature at hand. If this was a PRG tree, if we go into the hash tree, I can use this to actually compute the root node. Different direction of arrows. Okay. And it is pretty straightforward to show that this thing is actually secure if the one-time signature scheme is secure and the hash function is collision resistant. Why does this hold? What kind of attacks can I imagine? If the attacker gives me a forgery after, in this case we can assume they ask for signatures under all the one-time public keys until the tree is exhausted. If they give me a forgery, if this is for one of the one-time public keys that was in my tree, this has to be by definition a signature on a new message, which means it's a forgery for the one-time signature scheme, right? And I can actually find a reduction which extracts this by guessing for which one-time signature scheme the forgery will happen, and so on. Of course, the second thing that an attacker could try is put a new one-time signature scheme into the tree. This would mean that the signature contains a one-time public key which was not in my tree. But then there has to be a collision by the pigeonhole principle. Because we have some path, let's say this was the forgery is also for position 2, and this value differs from the one-time public key in position 2 differs from the one-time public key that I actually used. But the overall public key, the root node, actually is the same, otherwise the forgery would not be valid. Right, so I have two paths that start from a different beginning but end in the same point. They must meet somewhere. You cannot avoid this, and the point where they meet is the collision. Yeah?
But you don't really need full collision resistant, right? Because one of the two inputs is not adversarially chosen.
Exactly. So actually you can, with a bit of work, get this down to second preimage resistance. This just makes the reduction a lot more annoying, because although intuitively this is the case, proving this is a bit nasty, because hash functions have this annoying thing that there's no algebraic properties or so with which you can do funny stuff. So you have to come up with some ideas, but we'll come to this in a bit. Okay, so Lambert scheme, actually the efficiency of this whole thing extremely depends on the one-time signature scheme. The trees don't take that much. Actually, most of the size comes from the one-time signature, most of the time comes from the one-time signature, because computing these nodes means I have to generate these one-time key pairs. pairs. Right? So essentially, to compute a signature, I have to generate all the one-time signature key pairs in the tree. And so you can actually do better than Lambert's scheme. So let me skim through this. If you look at how a one-time signature for Lambert looks in the tree mode, you have your signature and your verification does first verify the one-time signature and then verify the authenticity of the one-time public key. And we can do better than this. The first optimization is I built a signature scheme where from the signature I can actually recover the public key. I can do this by including additional information to the signature, which in the first moment might seem stupid because you're blowing up your signature, you're actually doubling the signature length. So let's say my first message bit is 0, then it will include here the secret key in the left element. But for the next signature element, I will actually include the public key value of the first pair. Right, so from every pair, I'm taking one secret key value, one public key value. This has the advantage that actually I just have to hash the secret key values in there in the signature, and I get the full public key. And so if I'm actually looking at what happens in the tree signature mode, I can skip the one-time public key. I don't have to include this because what I can do is I do an implicit authentication of step 1 using step 2. So I compute a one-time public key from the one-time signature. And then I verify this computed one-time public key via the tree authentication. So I use the authentication path nodes, I compute up to the root, check if the roots match, and if these match, then this must have been the one-time public key from this position up to collision resistance of the used hash function. Make sense? And you can even do better than that. So German's law of Ordnung, I mean maybe not so much, but you can start sorting these things. So I just take 2 secret key values, and then I encode my message as my message, and like the original message bits, and the negated message. And then in the signature I include the secret key value if a bit is 1, and the hash, so the public key value, if the bit is 0. Right, so I will actually include half of the secret key values, half of the public key values, as before. Now if you look at this, this thing is just a checksum with really bad performance, because I'm just putting there the same message again in negated form, but it's just doubling the message. And we do not need this. So the thing that we need, actually go here, is that whenever someone flips a bit in the message, some other bit in the encoding, well, whenever someone flips a bit from 1 to 0, so instead of the secret key, you only have to include the public key, some other bit in the message encoding has to flip from 0 to 1. Which means I actually suddenly need a secret key in some position where I previously only saw the public key. Right? And I can do this using a far more compact encoding, namely, I take the inverted Hamming weight of the message. So I sum up the bits of the message and then negate the result represented as bits, or represented in binary. And if you think about it a moment, you can see whenever I am flipping 1 bit in the first half to 0, the sum will go down, which means at least 1 bit in there changes, and with the negation it will actually go in the right direction. And you can play exactly the same game the other way around, so whenever I flip 1 bit here, from 1 to 0, a bit here has to flip from 0 to 1. And it can also, these cost them. And this means I actually just need m plus 1 plus log m elements in my secret keys. And for example, for parameters that we usually use, this is, you're going from something like 128 or 256 to 9 or 8 bits. No. You go from 256, you go from 512 to 256 plus 9. So 265. So you're almost going down to half of it. The reason that I actually don't have these numbers in mind is that this is still not the thing that we're actually interested in. You can do this in an even smarter way, and this is what Winternitz proposed. If you have your function family, you can build what's called a hash chain. And the hash chain, the most trivial thing is just I'm reiterating the hash function on an input, right? So I call the hash function on the input, then I call the hash function on the result, then I call the hash function on the result, and so on. And if I look at the intermediate results, then this actually gives me a chain of values. The zeroth value of this chain is the input itself. And if I have a chain of length w, then the wth element, which is the chain evaluated w minus 1 times, is then the hash function w minus 1 times called on x. And the nice thing is, of course, whenever I give you a node in this chain, you can go forward, but you cannot go backwards. And so the Winternitz signature scheme takes a bunch of random values. So these are L values. This is essentially the m plus log m plus 1, but reduced by a bit, which we'll understand in a second why. And then builds length w hash chains for each of these random values. My secret keys or secret key values are the starting points of these hash chains, which are just random values, and my public key values are the endpoints of these hash chains. And so how do I sign put this? Well, the basic idea is, again, I'm publishing some hash values or random values, but how do I select them? I start with my message. I represent my message in base W. So if I have, for example, a binary message, I take W to be 16, then each of these B elements is a 4-bit string, and I interpret this as an integer between 0 and 15. And if W is 16, I have chains of length W, so chains with 16 nodes. I compute a checksum, and it's essentially the same as before. It's again the negated Hamming weight, but now extended to elements of base W. I represent the checksum again as base W elements, and then I'm selecting the b'ith element of the ith hash chain and put this into my signature. Right? So if this was a 1 as an integer, I would take the first node. If this was a 0, I would actually output the secret key value here. If this was a 15, I would publish this value, and so on. And so my signature consists of L of these intermediate values, where L is the length of the encoded message. So the message plus the encoded checksum. And if I want to verify this, the verifier knows the message, the verifier knows W. So the verifier can recompute this message encoding. So this means they know which position in the checksum and the hash chain is actually corresponding to each of the signature values. And so they can complete this chain by simply evaluating the hash chain on it the respective number of times, so W minus 1 minus BI, and then compare the result to the public. Or or delay this verification if you're on the tree signature scheme. Any question about this? Yeah.
Is the checksum then enough to guarantee that the signature can't be forged by hashing for it?
Yes, so that's like in this case, the checksum guarantees that whenever one of the BI values increases, then there's another BI value that will decrease. Right? So whenever, if you think about it, starting from some signature, if you want to get to a signature for any other message, well, if you would decrease a B value in there, then you anyway need a pre-image in the chain. And otherwise, if you're increasing one, which means I get to a node which I actually can compute from the signature, it will be ensured that you will have to find a pre-image in one of the other chains. And in practice, you can actually just use hashing the values, then you get security based on collision resistance. You can also do something a bit more complicated where you're XORing in every round a random element into the hash chain. And so you've got one random element per level. Then you can actually get a reduction from second pre-image resistance. In both cases, you need one witness and undetectability in addition. And these bit masks are exactly what allows you to actually place a second pre-image challenge in the chain and get the adversary actually to find a second pre-image for you. So, yeah, so this is what this says. And the rough idea is an attacker actually doesn't have to give you necessarily a pre-image of the chain of the hash function for one of the signature values, because they might actually find a different path which branches from your. So if this is my signature value and this is the chain, they can come up with a new signature value which is actually not identical to this one and which will not hash to this one, and just merges somewhere here, but all in all gives you a longer hash chain. Right? And this still will mean that there is a second pre-image, there's a collision somewhere here with a not by the adversary chosen value, which means there's a second pre-image. And I'm happy to discuss this later if someone's interested. Okay, and then I can use this trick again. I get the public key actually from the signature, and I can delay verification to actually verify that the public key value of the tree that I get is the same that was in the public key that I obtained from the signer before. Is this clear? No reaction? Okay. So, XMSS is essentially exactly the scheme with some optimizations. So this WOTS Plus was one part of this. So this WOTS Plus where you don't need collision resistance. There's a similar trick for the trees. So if you include bit masks into the trees, so if you're XORing a random value at each level, then also there you can actually extract, can use the collisions to find second pre-images by placing second pre-image challenges in the tree. And so you don't need collision resistance there. You can, well, you're not signing directly messages because this would mean that your message length is actually limited by the number of chains of the internet signature scheme. So what you're actually doing is you take your message, you hash it, and then you're signing the hash. This would usually require collision resistance. However, you can do something that's called randomized hashing, where you put a random value into the hash function together with the message. This prevents collision attacks, because if you think about how a collision attack against the hash and sign signature scheme works, if I find a collision, I can ask you to sign the one half of my collision, and afterwards the signature will also be a signature for the other half of my collision. Right? If I have two messages that collide under a hash function that is used in the pre-processing of the signature scheme, then this gives me immediately a forgery. If the signer includes a random value, a collision doesn't help you anymore because you would have to predict the random value that the signer uses. So if you have a collision that only works if when you're asking for a signature, this random value is actually part of your, or was part of your collision. And so this means with these few changes, you actually get a collision resilient signature scheme where you do not need collision resistance anymore. And if collision attacks don't apply, this means we actually can halve our signature size because our signature is just hash values, right? So everything that goes into the signature are nodes of the tree, random values of the length of the hash function, or intermediate values of these hash chains, which are all hash values. And if these only have to be B-bit messages instead of 2 B-bit messages, I have my complete signature size. And in addition, I have some pre-warning system because usually, well, the hash function is somewhat established. They will first break collision resistance before they go for a second pre-image or pre-image resistance. The second thing that was actually already introduced before and then reused in XMSS is the following thing. During key generation for XMSS, I have to generate all the one-time signature key pairs. So if I want to be able to use a key pair for many signatures, I have to make my tree quite large, and I have to generate as many one-time key pairs as I want to do signatures. So if I go for something like 2 to the 60, this will take a moment. What I can do instead is I built kind of a little CA for myself, or a little PKI. So I built layers of trees, where the tree on top is used to sign the root nodes of trees on the next layer, and so on, until on the bottom layer you're actually signing messages. And then, well, I got essentially a certificate chain, right? So my signature will then contain a signature of the message on the bottom layer, plus the authentication path, plus the signature of the root node using the next tree, and the authentication path in there, and so on until I arrive at the root node of the highest level tree. My public key will just be the root node of the top level tree. And if I'm doing this, I could in theory just generate the top tree in the beginning. That would be enough for key generation because I need just this one root node. However, for the first signature, I would have to generate all the leftmost trees if I'm walking through this hypertree from left to right. So actually during key generation, you usually would generate all the leftmost trees. And then you're generating the next trees as needed. So you can distribute this in a nice way so that for every signature, you're doing about the same amount of work and you're preparing next trees as you're using the current trees, and there are nice algorithms to actually do this. And then, so key generation goes down from 2 to the h to d, for d layers down to d times 2 to the h over d. And actually also the signing time goes down from h over 2 to h over 2 times d. Of course, this also has a disadvantage, namely I'm paying with the additional signatures, right? I have to link the layers, d minus 1 additional signatures. Any questions about this? So this is all relatively old. I was working on this stuff during my PhD, by the way. Pick your PhD topic wisely because you will be stuck with this for a very long time. What we looked into at a later point is the moment you're going away from collision resistance, your suddenly talking about targeted properties. So finding a preimage for a one-way function is hard, but if you have many possible images and you have to find a preimage just for one of them, your success probability for every guess grows linearly in the number of images that you have, right? Because if I, for example, if you look at a hypertree of a total height of 60, then on the bottom level, I will have 2 to the 60 Winternitz instances. If I use Winternitz parameter 16, then I will actually have 67 chains per Winternitz instance. So I have a total of 2 to the 66 images that I will actually see in Winternitz signatures on the messages, ignoring the images that I see actually in the higher areas. Whenever I can find a preimage for one of these, I potentially have an attack. Right? So this actually means my attack complexity goes down by a factor 2 to the 66, which is quite a bit. So if before my success probability doing Q queries was Q over 2 to the n, it's now Q over 2 to the n minus 66. We're talking about usual values of n like 256, so we're suddenly going down from 256 to actually 190. That's quite a decrease, and this is something where people are not very happy with. And even in the quantum case, there actually multi-target attacks don't have that much of an impact, because the square, like the complexity is actually the, so you don't reduce the probability, but you're increasing the impact of your queries. But so you actually just get a 33 bits advantage quantumly. But still, 33 bits is actually too much. And in end of 2015, I think we looked into this. Now we can deal with this. And the idea is actually that you use something like domain separation. So this is something that is by now implemented in different ways in different schemes, but in general, the idea was that you're assigning every hash function call in your total structure an address, and such that these addresses are unique per node. And thereby, you can actually, you have to commit to an address. Oh, okay, so these actually become input to the hash function. And then what happens, you can think about this like if you have a bunch of dartboards next to each other, I can just throw and I will likely hit one of them, right? If I'm spreading them out around the whole room, I have to commit to an actual dartboard that I'm aiming for. But I mean, I might still hit the next one in my case, but I will not hit the one behind me if I'm throwing it forward. And so I can do this actually in a way that I'm forced to commit to which dartboard I'm aiming for. So I'm forced to commit to which image I'm actually looking for, and then my complexity again goes up to Q over 2 to the n, or Q squared over 2 to the n in the quantum case. And this taking in the address is something that we hit in an abstraction called the tweakable hash function. And this takes public parameters. So this you can think of as the function key. A tweak, which is the address. So this is unique per hash function call. And then the message, and then maps to message digest. And then we have security properties which are more or less similar to second preimage resistance, one-wayness, undetectability, and so on for these tweakable hash functions. And the actual properties or the bounds that you get are determined by how you actually build this tweakable hash function. And I think I'm short on time, so I will speed up a bit. So these schemes are by now standardized for XMSS. There's an internet draft. So this protects against multi-target attacks. So there's a tight security proof, which had a tiny flaw in it, which we will now fixed again. But you get, from n-bit hash functions, you get roughly n-bit security. You have pretty small public keys, so you need 2 n-bits here. This comes at the cost of a QROM proof, because you need all these bit masks. And actually, if you want to, so you can either store them in a public key, which means you have number of nodes in your full tree structure of elements in your public key, which means you're going into the dimensions of Merkel's, which you can discuss about if this is practical or not. Merkel's not listening. But if you don't want this, you can actually, these are random values, so you can pseudo-randomly generate them. This is what anyone would do in practice anyway, right? So locally they will pick a seed, they will use a PRG, and generate all these values, put them in a public key. Now you could say, no problem, I'm just handing out the seed to everyone, and they can generate them themselves. I don't have to put them in the public key and send them around, they can do the computation themselves. The moment you do this, your standard model reductions don't work anymore, and to get a reduction working again, you have to switch to random work model. It's a bit annoying, but that's what it is. And we have instantiations based on SHA-2 and SHA-3, and the scheme is more or less the same as in the XMSS-T scheme, which we published in PKC in 2016. Up to some details on the message digest. Yeah, so for runtimes, the public keys go down quite a bit. This is exactly why, because we don't have to include the bit masks anymore. And these are height 20 parameters with a single layer, so that's 2 to the 20 signatures. These are 2 to the 60 signatures with 3 layers. And you can see actually signing and verification times, okay, only at the signing times. They are pretty reasonable, they are in the amount of a few milliseconds. Verification times are significantly faster. But the signature sizes for the 2 to the 20 are still somewhat reasonable, so 2.8 kilobytes. It's not RSA or elliptic curves, but it's not totally horrible. If you have more layers, then this actually grows. I mean, these are essentially 3 times 2 to the 8. Right? What else did I want to say? Right, and actually, one thing that I will not manage to explain in the lecture because I don't have the time. The secret key is not just a seed. If you want the stuff to be fast, you need algorithms which keep some state to compute these authentication paths efficiently. Right? If you think about, on average, every time you're changing the authentication path, one node will change. So if I'm just storing the last authentication path that I used, I only have to compute a new leaf, and every second time a bit more. And I can do this in a nice way so that this is not too costly. But that's it. The last thing that you see here is that you have a factor of 3 between traditional XMSS and XMSS-T. And this is because XMSS-T generates these bit masks and actually fresh function keys pseudo-randomly from the addresses. And that is 2 additional hash function calls. A different approach was proposed in the LMS proposal, which is also in RFC by now. And what they do is they say, yeah.
So but if I followed this correctly, this is still a few times signature, right?
This is still,
so how many?
We call this a many times signature.
Yeah.
Because we will have few times signatures later.
Okay. That's quite a many times signature. So how many signatures is this about? Like the numbers you showed?
As I said, so here the top 2 are 2 to the 20 signatures per key pair. The lower ones are 2 to the 60.
Oh, okay.
mean, 2 to the 60 is virtually unlimited. I think there's hardly anyone that does this within the lifetime of a certificate. Because you should not use the same certificate on all servers, in my opinion. So LMS is essentially the same scheme from a high-level perspective, so the structure is exactly the same. The difference is that the hashing is implemented differently. They just go full random oracle model. So XMSS had this idea that you can still get a standard model proof if you're actually pseudo-randomly generating the keys and the bit masks, and then you do this XOR padding for the inputs and so on. I don't describe all the details. LMS just takes the domain separation values together with the message, concatenates everything, hashes. That's fine. You get a standard model proof for XMSS. As I said, if these bit masks and keys are actually chosen at random and part of the public key, if you're generating them pseudo-randomly, you get a QROM argument for this path, which I can also hide in an assumption if I prefer. In the LMS case, I get a QROM argument for the full thing, and that's unavoidable. And in both cases, by now, I actually have tight security proofs. And LMS is essentially at the time complexity of what I had for XMSS before, so this gives me a factor 3 faster. But if I'm adopting signature levels, security levels, then you will have slightly larger signatures at the same security level. But this is a bit peanut counting, so it's a bit more of which assumptions I want to make. As I said, there was a slight slip in the security proof, and actually last year in crypto we fixed this proof for XMSS and also verified it using EasyCrypt. This is something that I think we don't have any time to go into during the school, but these proofs for post-quantum crypto tend to get even more complicated than the proof for the traditional crypto was, and we're working with math that we're not that much used to so far in cryptographic proofs. So these are error-prone, and we're finding smaller issues every now and then in the proofs, which do not invalidate the security, but just say the proofs don't hold. And so there's actually, during this week, another workshop on the top level of this building, where people work on tools that allow you to formally verify these proofs and convince the computer that these proofs actually hold. And this is what we did for XMSS, and we're currently working on doing this for Sphinx, which I will talk about next. And give me 2 minutes to drink something, and then I will talk about Sphinx. Okay, I hope I get through the rest. So, Sphinx. As I said before, the schemes that I talked about so far, they are stateful, right? I need to use these one-time signature key pairs in order to make sure that I'm not reusing one, because if I'm reusing one, I'm actually in trouble. So you can show that there's not much security left at that And so this works actually great in some settings, if you have the scheme implemented on a smart card or in some controlled environment, or you do this somewhere where you anyway know you have to keep track of signatures, like in a root CA or so. My opinion, perfectly fine. Other people are still a bit scared of this. Well, you can debate about this. What you cannot debate about, there's a lot of scenarios where you really have to stay away from this. So anything where you're in a VM, where you have automatic backups, where you're doing multi-threading of crypto, where you do load balancing, you don't want to use this stuff. It's so easy to shoot your foot with this. This is really terrible. Because the moment you're playing in an old backup, maybe without noticing it, you're reusing a key state from some time ago, which means you're reusing a one-time key pair, and you're doomed. And so in 2013, we set out to eliminate the state. This was beautiful. It was actually in Egypt, next to the Gizeh pyramids. This is why this is called Sphinx. And there were already tanks on the streets because the Friday after the next revolution they started. So, yeah, anyway. We made it out alive. Oh, good. So, actually eliminating the state, other people did this before us. For example, in 2000, so this goes actually back now on Young had a proposal in '89, and then the real stuff that we are building on is something that Goldreich proposed in 2004. And the idea is, look, what I can actually do is, I built a massive certification tree. So a tree where you use a one-time signature scheme always to sign two other one-time public keys. Right? I make this tree large enough. And then if I want to sign a message, I just pick a random leaf, use that one to sign a message, and include the authentication path in there. And include the signature path in there. The only thing I have to make sure is that I don't have a collision. I can reuse the intermediate thingies, because if I generate them pseudo-randomly in a deterministic fashion, I will always get the same keys again, so I don't have to store these. And still, I will always sign the same one-time public key, so this is all fine. But of course, if I'm using the same leaf twice, I'm doomed. So this means, to get the probability of a collision small enough, if I want 128 bits of security, I would have to actually build a tree of height 256. You can play some tricks in there. If you just do this, you end up with several megabytes of signatures, so this is something that you don't want to do in practice. Yeah. So, but you can actually play a few more tricks, and then you arrive at what the Richard Sphinx proposal was. Namely, you can see this as a hyper tree, so a tree of trees, where the number of layers is the height of the full tree. Right? But you can do some intermediate values. So if you roughly take, I think it's the log of the height as the number of layers, or in the case of Sphinx, we used 12 layers of trees of height 5, then you actually get something which gets more reasonable. And the second idea is, this goes back to people from the Tau Labs project, that you use something called a few-time signature scheme on the bottom layer. So this is a signature scheme where you can do, in our case, something like 8 to 9 signatures with the same key pair before your security slowly goes beyond the security level that you're actually aiming for, and really slowly degrades. It's not that if you do the 10th signature, you suddenly have no security at all, but it really slowly drops. And this means we actually can have some leaf collisions. Right? It's not that bad anymore. We just have to make sure that they do not collide too often. And this allows us actually to reduce the tree height quite a bit. And so, as I said, I think we had a total tree out of 60, and then a few time signature scheme where you can do something like 8 to 9 signatures before security goes below 128 bits, and then that was actually fine. So let's briefly talk about what a few time signature scheme is, or how we built one. So remember, we had this Lampert-Diffie one-time signature scheme, and there, if you're using this too often, namely twice, actually all security is gone. But I can actually use a very similar structure, and this is by Racine and Racine from 2002. They call this horse. And so here they're using a collision-resistant hash function in addition to the one-way function. And what they do is they first generate a secret key string of t random n-bit strings, and well, t will become clear in a moment. And you do, as before in the Lampert scheme, you hash these, and the resulting values will be a public key. And you will actually publish several of the secret key values as a signature. Now this t is actually here.
So I have a question about the breaking the Lampert scheme. I mean, if you're gonna put your message through a random oracle in the first place anyway, you still have to find the correct message that will output the thing, right? So
this is perfectly true. If you're first hashing, then it's not trivially broken. After seeing 2 signatures, we had a paper called, oops, I did it again. Was not my idea. At that time, we needed a funny title to get a paper. Anyway, there we analyzed this, and you have to keep some security, but it's something like 2 to the 30 complexity. So this is something that you then still can break within a few minutes on a modern machine. But the idea is kind of the same here. So what you do is you take your message, you feed it through a hash function, and then you get something like a 256-bit string, for example, and you split this into k blocks of log t bits. Right? So every of these blocks actually will give me a number between 0 and t minus 1. And so these I can actually map to my secret key. Right? So each of these values picks, come on, one node, one secret key. These can collide, so it can be that I pick the same secret key value twice, 3 times, 4 times. This is actually a bit of an issue with this version of the scheme. They are unsorted. It doesn't matter if the first index picks a certain value or the third. You will just have a set of these secret key values which are indexed by these by the hash, and then you publish these. Right? And I can verify these. I can recompute the hash value. I can recompute the indices. I have the public key value. I can just check that the values in the signature hash to the respective public key values, and I'm fine. And the security of this thing goes back to something called cover-free sets. So with cover-free sets, an R-cover-free set is after seeing R subsets, their union will not cover any R+1 subset of a bigger set. Right? And here we have kind of a computational version. So every message gets mapped to a k-element subset of the secret keys. And I'm in trouble the moment that I know so I'm in trouble the moment I've seen R signatures for one horse key pair, and I can find R+1 messages such that the R+1 message maps to a subset that's fully covered by the union of the previously seen signatures. right? And this is actually, I can tweak the parameters such this is still hard, but you can see here this arrow points at the R. So the bigger R gets, the lower the security gets, because the easier it gets to actually find such a set. And so that's why I have to actually keep the R somewhat low, but at the same time you see this does not immediately go to 0. So as R grows, it's just getting easier. Right. And then the first thing we did is, well, we love trees, binary hash trees are great. So what to do? Well, drop another key on this thing. And so Horst was essentially is horse, but with trees. And what we did is, with some additional optimizations, instead of you have this full public key, you again put a Merkle tree on top, you just put the root node as the public key, and then you publish authentication paths with the secret key elements. And you can do some tricks because these authentication paths will start to overlap or cover the full tree at a certain point or a certain level in the tree. And then you can play some tricks that you're not including all nodes there and so on. And I don't have to have time to go into this, but in our case, we published an intermediate level of the tree entirely and only had authentication path up to there. There was a competing proposal called Gravity Sphinx, where they actually really computed which nodes can be computed from multiple authentication paths, and then they skipped these and so on. But then you get variable size signatures, and so we skipped this. The second thing we did is we actually used randomized message hashing there, which significantly strengthens the security, because again, the adversary cannot freely search for covers, but actually has to collect signatures, and then after seeing these signatures can start doing hash queries and see if any of them is actually covered by the sets that they obtained. Yeah, and so Sphinx combined these things, so in some sense you have XMS SMT used to sign a bunch of Horst instances, and we do pseudo-random index selection, so every time you have a message, you run it through a PRG, PRF, secretly keyed, and the output will be the index of the leaf that you will actually use. The thing is collision resilient, so we don't need anywhere collision resistance of a hash function. We get a deterministic signing procedure, which means you don't need a strong random number generator during signature generation. And at that point, we add for 128-bit security against quantum attackers. And we were able to get a scheme which has like 40 kilobytes of signatures, 1 kilobyte keys, because we still used including these bit masks in the keys. And using some tricks, you don't need 1 bit mask per node, but just 1 bit mask per layer in the tree. And you could do, I think it was at that point something like 200 milliseconds per signature. And then the NIST competition came, and we started working a bit more, and we came up with Sphinx Plus, which will now be this SLH DSA. They really butchered everything. And what we did there is we strengthened the security of the scheme, and then used the strengthened security to reduce the signature sizes. We added this multi-target attacker resilience. We went for fixed length signatures compared to this Gravity Sphinx, which went for variable size signatures, but in the end we got the same medium signature size. The schemes, if you look at this security level 3, has really small keys, so we've got 5 12-bit keys, and you have medium signature sizes, so in this case about 17 kilobytes. You can actually go much smaller if the number of signatures gets reduced. So there's currently a debate, there's some papers on ePrint that, for example, show that if you go for key pairs that will only be used for something like 1 million signatures or even 1 billion signatures, then you can go significantly down. I think it was something like 6 kilobytes or so. I would have to look up the numbers, but it really goes down drastically. And even because Horse doesn't immediately lose security, if you pick the parameters right, it is such that even if you're overshooting by a factor 2 to the 10, you still don't drop significantly below 2 to the 100 security. So, well, if you're overshooting, you lose security, but it's not in a really critical way. And our advertisement at this point was this is the conservative choice, right? So the lattice people are still fighting about what's the right size of parameters for Kyber. I mean, this debate might be minimally politically motivated, but in the end, there is still enough room to actually start a debate. And, well, this did not happen to us. So what did we change to strengthen security? Well, we dropped a few more trees. We went from Horst to Force, which we have Peter on the team. You can actually spell in a nice Star Wars way. Things are nice. If you remember, I said before we had in Horst, every index you don't know, a secret key element can appear multiple times, and you don't know, make a difference if it's selected by the first index, the second, or the third, and so on, which means it's actually easier to find a cover. And what we did for Force was, instead of using one big tree, we used a few smaller ones. And the first index actually picks a node from the first tree, the second index picks a leaf from the second tree, the third row from the third tree, and so on. Which means you suddenly have an order established, you don't have the same secret key element suddenly if an index occurs twice, and so on. And it actually strengthens security, and you can trade this then again for smaller trees and balance this out such that you actually can shrink the signature size in the end. A second thing that we did was we made the index verifiable, which means an attacker, when doing the forgery, cannot freely choose the Horse key pair for which they have seen the most collisions. But every hash query they do to actually find a cover will also, in the case of Sphinx Plus, tell them under which index this will be. And so you go to a slightly more complicated version of this subset resilience. We call it interleaved target subset resilience. And that is actually significantly harder to break than the subset resilience or target subset resilience that you need for Sphinx. That's what I just said. Okay, then in Sphinx Plus, we essentially added an LMS version. So if you look at the original Sphinx, you can think about this as an XMSS version of looking at how the hashing is done. We added an LMS version which just takes the addresses together with the public parameters and the message, concatenates things, hashes it, be done, and be happy with the random oracle model argument. And this will actually be the one that will be standardized by NIST. So the latest thing that I know of is that they will actually not standardize the robust versions. And then if you look at the outcome, you get, for every security level, so this is security level 1, 3, and 5 for NIST, we decided to do 2 different parameter sets. One set focused on fast signing, and the other one focused on small signatures and fast verification. And so the small parameter sets will be the most interesting ones in, I think, 99% of the use cases. So there, if you're at security level 1, which is equivalent to the security of AES-128, then, actually these are a bit older numbers, we found a bit nicer parameters which just go under 8 kilobytes for the signature size. At level 3 you're at 17, and at level 5 you're at about 13 kilobytes for the signatures. And if you look at runtimes, if you compare this, it's a bit hard to compare. So we actually get better than the original Sphinx proposal if you do a fair comparison in terms of size as well as in terms of speed. The only thing where we slightly increased was the signature verification time, and also if you compare to Picnic or to Gravity Sphinx, we actually would beat them in several metrics. And I managed to stop at half past. So I do not have the latest numbers for these on the slides. But to conclude, the nice thing about these schemes is they will never be the fastest, they will never be the smallest, but they are not terrible in terms of performance. They are, if you're signing software, if you're signing emails, usually this will not be the thing that blows up your sizes. And we do not need any new assumption to build these signatures, right? If we have a secure hash function in the sense of this behaves like a random oracle, then these things are secure. And actually the student of mine just showed that under certain assumptions, if you have a secure instantiation of ECDSA, then actually you have a secure instantiation of XMSS. Just using the hash function ECDSA uses internally. And the assumptions are just about the way how ECDSA uses the hash function, because some things are a bit underspecified. If you can live with the state, so if you have a setting where you can make sure that there are no copies made of your key, and this is really just used by one process, and you can keep track of your signatures, then actually these stateful schemes are pretty nice. They are relatively small for possible signatures. They are also significantly faster than Sphinx, and so these are a nice alternative. And if you're in any setting where you cannot guarantee this, let's say PGP email signing or something like that, keys on a personal computer, then you can go for Sphinx Plus, and that will be out any month now. I mean, let's see how long this takes. And that's it from me.